Sorry, I keep getting interrupted here. So what we were doing, we were looking at how to compute how the mean absolute error changes when you change each one of the absolute errors. So we saw over here that that whenever we took any one of these, so here are all the absolute errors. So here is one. If we were to take this one and wiggle it up and down a little bit, how much would the total, would the overall mean absolute error change? Well, we'd the sum of these errors, it's going to, if we wiggle one of them by a little bit, it's going to change the sum by the same little bit. And then we'll scale that whole thing by 1 over n. So any one of these errors, if we increase it up or down a little bit, it's only going to change the mean absolute error by 1 over n of that little bit. So each one of them doesn't have a huge impact. In fact, the more data points we have, the less of an impact each one of them has. That's what it means that this is a 1 over n scaling here. So let's see. So how would we write that out? Well, we can just look at our intuition here that whenever we change the one of these absolute errors, that changes it by way of how it changes the sum. So we can say, okay, we've got the we're going to be able to take the mean absolute error by something else. We'll fill that in a moment. But what we do know is that when we change, what happens when we change the each one of these? How does the sum of the absolute errors change when we change each one of the absolute errors? So that's what we just looked at here. When we wiggle each one of these individual errors up and down by 1, how much does the sum change? And it changed by the same amount. So we can see that the sum of the absolute errors, this amount of change, how much did the sum of the absolute errors change with respect to each one of them? That's just 1. However much the absolute error change, the sum changes by the same amount. So this whole thing here is equals 1. Now, all you gotta do is fill in what goes in here. So let's look at, remember your chain rule from calculus? It just basically means that we can almost imagine these d's as things that we can multiply and cancel out. It just says that we can't just assume it's going to work because these are infinitesimals, but it tells you the conditions under which it will work. And it basically always works. So d, just thinking symbolically, if we wanted d MAE over d absolute error, then and we have d sum absolute error of absolute error, all we just need to do is sort of cancel out that d sum absolute error. So if we were to write it down here, that kind of cancels it out. So this is the chain rule decomposition of a derivative into 2 parts here. And we know what one of them is. It's 1. And actually, we know what this one is too. dMAE over dSA. Have you seen that before? Well, it's just that. So, if you were in a calculus class, you'd substitute in 1 over n here. But we're in a programming setting. So what we can do is, instead of having to substitute in and recalculate it, we can say we already calculated it. That was some absolute error grad. So whatever that was, we can take our some absolute error and say we just multiply it by 1 to get our absolute error grad. And that would almost be right. We're really close. But what does the absolute error grad look like? What did our absolute error look like? It wasn't just one number, it was a bunch of numbers. So its grad is also a bunch of numbers. And that's just telling us if we look at it, it should make sense. Because this is, if we change this number, the first error, if we change this one by 1 wiggle, then the mean absolute error would change by 1/100th. Same thing for the next one, and the next one, and the next one. So every single one of these absolute errors has the same mean absolute error, or has the same impact on the mean absolute error, 1/n. So now we can start thinking, how is PyTorch actually computing these grads? Well, so this one was pretty simple here. We were doing, if we kind of imagined our overall wiggle as 1, then our sum absolute error grad is just 1/n. So let's just check that we've got that exactly the same. So there's 0.01. Okay, this is a tensor. Let me, well, we'll see in a moment how we can just collapse things, so it's so I don't have to tensorize everything here. So now, how do we compute the absolute error grad? Well, here's our sum absolute error grad. Here, this is exactly what it means for sum absolute error grad right here. So if we wanted to use this to compute our absolute error grad, which is this one, or this one right here, looks like we just take this and multiply it by a bunch of 1s. So we could take our sum absolute error grad and multiply, let me just do multiply by torch 1s, and 1s in there. There's our 100 1/10ths. So, and then that gives us the sum that gives us the absolute error grad, which is the same thing as we saw here. So that's how Torch computed this absolute error grad. So now let me keep going here. It looks like we got a good thing going here. So let's see how does, so really we want to get the how much does mean absolute error change when we change W and B, but we're getting closer. We're working our way up here. So we got mean absolute error grad. We got our sum absolute error, absolute error. You can think of these as all sensitivities, like how sensitive is mean absolute error to a change in sum absolute error? Well, 1/n of that. How sensitive is it to a change in the absolute error? Well, 1/n for each one of the items in it. And now, how sensitive is it to a change in the error? So let's think about what that would mean. So if we were to increase, let's wiggle this one up a little bit. So that's going to increase the absolute error up, and then we've just figured out how much that is. That's already just 1/n. But if we wiggle this one up a little bit, this the one that was negative, then now that decreases our mean absolute error. So this gradient was 1/n. This gradient is negative 1/n. So when we went through that absolute value function, that flips our that flips the negative, that flips the signs of any ones that where the error was negative. So it's basically saying that, well, how would we write this out? So the derivative, or the derivative of the absolute error with respect to the any one of the absolute errors with respect to the error at that one is, well, it kind of depends. If it's if it was positive, then that derivative is 1. So 1 if the thing was positive, and negative if that error was negative. Now there's a function that gives us exactly this: 1 for the positives and -1 for the negatives. Sine. The whole thing is sine e pi. So let's just look at what that is. So let's just see if we were to look at the absolute error grad, we see some negatives and some positives. And let's look at what our error sign is, and there's negatives and positives. So when we compute the gradient of this, we're looking at what is our error grad. Well, it's our error sign times the absolute error grad. So got the same thing. So that's our error grad. Okay. So now we've gotten to an important place. We know how much we need to, or how much any change to the error that we get is going to affect the mean absolute error that we end up at the end. So it might be worth kind of simplifying and regrouping here. So we've, let me delete this cell in the middle here and merge these, Shift M, merge these all together. So now we're trying to compute the error grad. And we're doing that by computing the absolute value of the error grad, and then which is itself computed as the sum error grad. Now, let's just pretend that we're an optimizing compiler here. We say, how could we write this expression more simply? We've already figured out how to compute it. Let's just write it more simply. So we could just, actually, let me just copy and paste it. So now I'm going to do some substitution. Now this is more of like compiler substitution, like a programming substitution, because that I'm going to do because I know I don't need this value again. So since this is just a constant, I'm going to pull it in to here. So I could say this is 1 over n. And then I don't need the 1 over n if I just pull this division out to the end. And then this simplifies even more because 1 times anything is just that. So here's our absolute error grad is 1's n over n. And then we don't need this intermediate value anymore after it. We're done with that. So we can move this into here. So now we're taking our sign times 1's over n. But here again, anything times a bunch of 1's is just that, so we don't need the 1. So this is error grad is just error sign over n. So we can check that we get the same thing again. Yep. So this is just a simpler way of computing that same thing. Okay. So now that we've got our error grad, now we can just keep back propagating all the way back through to our bias and weights, and that and we'll get what we want. So we want the how sensitive is the mean absolute error to a change in the bias, and we'll use the chain rule down here just like before, except we know what the sensitivity is with respect to the errors. So we know the mean absolute error sensitivity with respect to any one of the errors. And then all we're going to need to do is figure out what's the sensitivity of the error as we change the bias. And, well, to get to that, well, we're almost there. All we need to do is backpropagate through this minus. So we're almost at the bias that we want. We just need to keep going here and say, what's the, oops, I skipped a step here. That's why. So we don't have, with respect to the error, we have with respect to the predictions. And then we know how the y-pred is going to change when we change our bias. So this is going to be what's easy to calculate. Now we just need to get what the the MA dy pred is. So we can just, you can keep going backwards up here. We're just working our way from the bottom all the way up. We've gotten here, the one over n, we got our sum, we got our absolute value. Now we just need our minus. So we're going to get how does the mean absolute error change as we change any one of the predictions? Well, that's going to be how much does it change when we change any one of the errors. So error I. So let's look at one prediction at a time, and then there's one error at a time. And then we're going to say how much does that, how much does the error change when we change one of the predictions. So again, since we were backpropagating, this part here came from, well, we just computed that. That's error grad. So now all we need is this part here, the error dy pred. That is given by, well, here's our equation that relates error and y pred. Well, if we change our prediction up, then the error goes down for that one. Error, the it's not the magnitude of the error. It shifts up or down. So it might be getting closer to 0. It might be getting farther from 0. But a increase in y pred leads to a decrease in error. So that means that this derivative here is just the derivative of this expression with respect to y pred, which is -1. So we can write that. So y pred grad, we can look at what that was. Notice that's all of the same things that we had before, just with the signs flipped. This used to be negative and now it's positive. Well, that's because y pred grad is just the negative of error grad. All right, now we're basically there, because we know how does y pred change with respect to the mean absolute. With respect to bias. Well, here it was right here. You can do the math here directly on these expressions, and that's actually what PyTorch is doing. It's just looking here at the expression. How do we compute error? Well, we negated y pred and added it. So our gradient, the derivative is -1. How do we compute y pred from bias? Well, we just added it. So the bias gradient is just, well, wait a second. So bias grad is one number. How do we get that one number from all of these y pred grads? There's a bunch of numbers here. Well, what happens to each one of these when the bias changes? Well, each one of them goes up or down by that same amount. So if you think about it, basically the sensitivity is the sum of all of these. So we're going to take the sum of all of the pushes up or down, and we'll see how what effect that has on B. So it looks like the derivative of any prediction with respect to the bias is 1. So our overall derivative is the sum of all of those. So we have our grad sum here, which matches our bias grad. So we've been able to figure out how we can write this whole thing without even having to use PyTorch machinery at all. So let's just demonstrate that we can win at this. So compute it all here. So we see our error grad is our error sign over n, because we were able to look at the over n from there. A summation didn't change, it gave us a bunch of ones, but we didn't have to change that. Then the gradient of this step was the sign, so here comes the error sign over n. And then we didn't actually need our ypred grad. We could just go straight from that to our bias grad, which is take our error grad, negative of that, and sum. So that was our bias grad. So it still has this grad function. They all still have a grad function here because we built it off of a tensor that told it requires grad. But we should be able to turn this all off now, and we can get this same thing here. So last little thing is that I would leave this as an exercise to the reader, but you've watched this far, so you get the bonus of seeing this. What is the what's slope grad? Well, slope dot grad, negative 0.2. Where did that come from? Well, how does each one of these slopes change? So the slope, how much does ypred change with respect to the slope? Well, it depends on what the corresponding x was. So for if x was 0, changing slope didn't change it at all. If x was 1, changing slope by 1 changes ypred by 1. So it basically is proportional to x. So we can do our same thing that we did before, where the derivative of ypred with respect to the slope is the same thing as the bias, which is basically as if x was 1 everywhere. Now we're multiplying by x instead here too. So we'll see that if we take our so I did need the ypred grad after all, because yeah, I prematurely optimized this ypred grad. So there's our error grad. If we take this ypred grad and multiply it by our x's, that gives us a bunch of numbers. We can take all those numbers and sum them. Just like we did for the bias, we'll sum up all of the contributions of each one of the data points, and that should match up with the slope grad. And there it is. So now we basically have slope grad. Except let me point out one thing. Here is a element-wise product of a bunch of numbers. So each number in ypred grad multiplied by corresponding numbers in x, and then we're going to sum the result. That's just a dot product. That's just ypred grad dot x. Or you can write it even this way, matmul operator. So there is our backprop. Backpropagation for linear regression. Now we should be able to turn off these requires grads, so we're not using the autograd machinery in PyTorch at all. We just get a single number out. We get our value out. I get to clean up all this other stuff down here. And so this is the way that we can compute each one of those things, each one of the gradients that we needed, the sensitivities with respect to slope and bias, and now we can use those to descend our gradient. And 1.592, backprop again, descend. 1.573, backprop again, descend. So let's just take this and put it in a loop. Let's do this 10 times and print our mean absolute error each time. And we can do, so this, we can call this the forward pass, and then this is backward pass. And here's our update. Here, so this is our take step. Take our gradient descent. So this isn't stochastic gradient descent because we're using the whole data set each time, but now here we go. So we're going to do this 10 times, and over the course of 10 times we have just gotten down to 0.48. So we are descending the gradient in the right way. Let me merge these together, and we can run this for, say, 100 times. And this is a constant, so we should pull it out in front. So we can tweak it here. You can see how fast did we want to descend. So what happens if we do too fast? Well, actually, this is a really tame problem, so we can go down pretty quickly. And there's our minimum mean squared error, or mean absolute error that occurs at our slope and bias of 3.37 and minus 0.68. So you can go put those into our here, 3.375 and minus 0.68. 3.375 and minus 0.6. Okay, I can't get quite there, maybe minus 0.7. Okay, so there's our line, our best fit line. All right, there we go.